You get to see me struggling. I hate that, but that's what it is. So anyway, we're going to go back and we're going to do chapter 5. At the end of chapter 5, there's some problems we're going to work on first. And then we'll go back and we'll look at the rest of it. Okay, so we're going to do problems 1, 2, 3, 4, and 5. And we're not going to do them all because some of them I really don't know what he's trying to get at. So I'll tell you the ones that I can do, and we'll go from there. So 5.1, sketch the following waveform, u of t minus u of t minus 3. So basically, this is your timeline. This is t equals 0. This is 1, 2, 3. So at u of t of 0, it goes to 1. So it goes up here to 1, and then it goes over to 3, and then it goes back to 0. And that's that first one. That's A. The second one is not much more than that. It's here's the timeline, and t equals 0, minus 1, 1, 2, 3, 4, 5. And this one is at t plus 1, which is right over here. It goes up 5. And then it goes at t minus 2, which is over here, it goes back down to 0. So this one goes up to 5 and back to 0. So this would be height of 1. This would be height of 5. The next one is minus 2 u of t. So basically this one is minus 2, which would be down below 0. Okay, so it's minus 2 u of t, and that starts at 0. So it's at minus 2. At t minus 1, it goes down another one. Excuse me. Oh my goodness. So at 1, at t minus 1, it goes 1, 2, 3. It goes down to minus 3. So it goes down to minus 3. And at t equals 2, it goes up 3. So at t equals 2, it goes up to 0. So basically it does this, and from that on, it's at 0. So it starts at 0, comes down to minus 2, minus 3, goes over there, and then comes back and goes to 0, and that's it. All right, that's 3 of them. Did anybody have any questions so far? So how do you do this minus t thing? Well, I think that you do it this way, but it doesn't really explain it very well, and I didn't try to make a big deal about it. But this minus t thing, I think it's just like this. So it goes this way. So it's 10, and it goes all the way back from time immemorial. So it goes like this. All right. I don't think that's a bad approach to that problem. I don't really care. That's not, usually you don't describe it that way, so I guess that's how you describe it. All right, so now let's do number 2. Everybody see what we're doing with these? They're not hard. They just take a little bit of time. All right, so number 2, 5.2. Everybody see that? So what does it do at t plus 1? Okay, so this is A. At it goes minus 10 at U, excuse me. So 5.2, I got to get this right. Minus 10 t plus 1. So the plus is to the left. Now, I go up at t equals 1 by 20. Okay, and there should be a u in there. Minus 10 u of t plus 1. Plus 20 u of t minus 1, which is that one. And then at 3, minus 10 u of t minus 3. So at minus 1, which is the opposite. Okay, so there's that. You go down 10, then you go up 20, and then you go down 10, and that's that. Any questions about that one? I'm going to let you do the other ones because I think you've got the idea. Okay, sketch the following waveforms. All right, now, so this one, this 5.3, is 12, so it's been on forever, so from time immemorial it's been at 12, and then at t equals 0, it goes down 2, so it was at 12 up to that point, and at t equals 0, it goes to 10, and there you are. Okay, so the u of t basically defines a period of time from starting at 0, and then it goes forward like that. B minus 2 u of t plus blah, 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 plus u of t minus. So this is a really short duration right at 0. So basically you have at t equals 0, you have 0.003 right here, and at plus 0.003 right here, and you do what? You go down 2, and then you go back to 0. So that's that one. This would be a minus 2. And that's 0.03 seconds there. This time is in seconds. Okay, so this next one is t. So this is a ramping function. So this would be at t, so c is what? So we start at t equals 1. So 1, 2. Okay, so at t equals 1, we start up a ramping function that goes up. Every second it goes up 1. So it basically looks like this. And then at t equals 2, we go back down. But then it continues. This t, if you, okay, and this is the function, this is the function, just a block of one, like this would be a block, this size, but because you say t in front of it, it becomes a ramping function and you go back to 0. So all that is that little triangle, that little triangle right there. All right, so this one right here would be of minus t, so it would be going this way. And these others are rate, and this would be a rate going up, and then at, okay, so this one, this 5.4, again, I'm not good at these. If you ever get a question from me on any of this stuff, it'll be something like this. I'm not going to get into the fancy ones, because there are really, you can have different opinions about some of this stuff. And I found, as I'm going through this book, I'm finding some mistakes that I just don't agree with. So anyway, if you ask me, what would I ever ask you to test? It'd be something like this. That's about it. Okay. So again, here on 5.4a, you've got r of t plus 2, which would basically be a ramp starting at -2, going up at a level. And when it gets to +2, it does what? It subtracts 1. So basically at +2, whoops, I don't want to that far. When I want to go just that far, -2 to +2. And then there's one coming down at that rate, so that one up and the one down cancel each other out, so you're basically flat. That's if you had a 1 in front of that, which you do. Minus, you have going up, and then you got one going down. And basically, this one cancels this one. Now, if you said -2r, you would have it going down. But you don't, okay? That's all that one is. So that kind of gives you a little bit of a flavor of that one. Now, this one is 4, which is from time immemorial down to, and then this is, okay, so this one's kind of interesting. B, this one's A. B is 4, which you've had that one going forever. So 4 is across the board, it's a 4. And then you have, on top of that, you have a rate at t plus 1, so you're starting up at that point. So at -1, you're starting to go up from that, and that at t equals 1, you're going down at that rate, and then at t equals 3, you're flat, because you went up, you came down, and now you cancel this out. So basically, whatever that r is, it starts at 4, goes up from that, and then it comes down and over. C, derivative of u of t. Well, in that case, it's just the Dirac delta, which is that. And the second derivative, I don't know. I do not know how to graph that. So you can wonder about whether or not your professor's any good or not. I don't know all these answers. And that one's not in the book, at the back of the book, so I really don't care. So anyway, now let's go through here and describe as a sum of singularity functions. Okay, all right, so at t less than 1, it's 2. Between 1 and 2, it's 4. And after, okay, t less than 1, t less than, between 1 and 2, and t greater than 2. So it's between 1 and 2, you're going to get this action. So from time immemorial, it was 2. So basically, you just say 2. You don't say u of t, because u of t starts at 0. So if it was always 2, you would just say basically, so for 5a, it was 2 all the way up till 1. So it's been 2 up until t equals 1, right? So this is t equals 1. And it jumps from that to 4 at that point. And then at 2, it goes to 0. Okay, so that's what we have. So basically, we write 2 plus 2u of t minus 1, which gives us that bump up, minus 4u of t minus 2, and that gives us the bump back to 0. Any questions about that one? That's this right here. And I'm going to let you, well, I'm not gonna worry about this one. I'm not gonna worry about this one. Um, those are the only ones I assigned. I didn't assign this one. I thought about giving you this as a quiz next. That's the quiz, that's the quiz, so that's what we did. Okay, that's what we did. There you go. So that's all I did, and that's your quiz. And did anybody have any questions about it? That was your quiz.
Could you cover it?
Huh?
Could you cover it? We turned it in today.
You turn it in? Okay, sure. So this would be from, okay, so again, I'm not, okay, so it goes 506 from -1, so it's 10 u of t plus 1 plus 10 u of t, and then that goes, and then I go to a ramp plus, I go from 20 to 40, so I go by 20 t u of t minus 1 minus, so I want to cancel this out, minus 20 u of t minus 2 minus 20 u of t minus 2 minus 20 u of t minus 3. Is that what you got?
One of those.
This could be an r, right? I don't care, r or t.
On the minuses though, does it just go straight down 40?
What's that?
So shouldn't one of the minus 20s have a T in there?
Yeah, that's what I'm saying.
Okay.
I bet on your second layer down, second one.
Like one of them cancels out the ramp and one of them goes down?
Yeah, you just wrote the same thing twice.
So this is the ramping one. This is the ramping one. 20t u of t minus 1.
Yep.
And then you have to cancel this ramping out. So basically minus 20 t. There should be a t. Minus 20t u of t minus, or 20r.
Okay.
I don't care. Okay. And then you have to subtract this out, which is this one. And then you go back to 0, which is this one. Yeah. So, everybody got that? Anyway, it's just how you describe things. That's all it is. Not a big deal. This is not a big deal. All right, now let's go on to chapter 6. Okay, so in capacitance and inductance, this chapter goes through that, and I'll go through this chapter with you. And then at the end of this chapter, we have some very interesting problems. And I assigned to you 1, 2, 3, 4, 5, 6, and 7, 15, and 16. So that is, I put that on your syllabus, and your syllabus is out on the website now. And I'll show it to you. Okay, so I've done some work on this, and chapter 6 is that, chapter 7 is that, chapter 8, and after chapter 8 we have our test. This may slip a little bit because of the snow, but that's what I hope to get done. After chapter 8, have a test, and then get into chapter 9, which is the Laplace, which is the hard part. So we're getting through some of the, I hate to say the easier part, but it is easier with respect to the stuff that's coming up. So be aware that this is just the beginnings of this stuff. Okay, so a capacitor and an inductor, you've studied it before, but basically this is what it looks like. That's a capacitor. Two metal plates, there's a distance in between them. There are no electrons that actually go from this side to this side. If there are, it's no longer a capacitor. Okay? So how does this thing actually work? Well, it stores here and then it loses here, it stores here and then it loses here. So basically it's a storage device. Here are various types of capacitors. I've worked with capacitors that are 70 farad capacitors that look like a suitcase. And there is a variable capacitor, little bitty capacitors. And this is the equations, and I'm not going to ask you to know all these equations, but I am going to ask you to know the one, which is I equals C dV over dt. So that's the one I'm really going to go with a lot. Okay, so again, this equation right here, which is I, this is the ice equation. If you remember me from other courses, I get into this ice thing and Eli, the Iceman, and I ask you to remember that. And here it is. It's I equals C dV over dt, commonly called ice. Okay? And if you can't remember this, remember this, and then you can put the dV over dt over instead of E and you're in. Okay? What's the other one? Eli, right? Eli the Iceman? Remember that? Have you had me before when I've talked about Eli the Iceman? Yeah. 1020, right? Any questions about that? So that gets you what? It tells you how you get current in a capacitor to pass through that device. You have to vary the voltage. You have to vary the voltage. And what kind of signals vary in voltage? Well, sine wave does, okay, obviously. So that's how you get a pass-through, even though you actually don't get passing through, you get them oscillating and store, unstore, store, and unstore, that type of thing. And this is the voltage is V equals the 1 over C integral I dt plus the original V sub 0. So basically, this would be my integral formula. So that gets you the two formulas. And this is the power. And that is a, So instantaneous power is this. And it's also this. But we don't worry about power. I'm not going to ask you the power equation. You can ignore it. If you can get this far, right there, that's as far as I'm going to carry this. So that gets you a little bit of an idea how these equations are going to be stacked up in this chapter. Okay. Again, these questions are interesting. I'm just going to go straight through them. And then we're going to get to the inductor. It's going to be the same thing, only opposite. We'll go down to the end of the chapter and we'll do some problems. I'll skip through the op-amp portion. The inductor. There is an inductor. And here is your famous equations after just a few minutes. Here it is. V equals L di over dt. Eli. V or E is equal to L di over dt. And the integral of di or I is equal to, excuse me, I is equal to 1 over L integral voltage dt. Again, this is the power. I'm going to skip the power. When you get into the power part of it, you can ignore it. Okay, so this is, again, it's first order differential equations is basically what it is. Here's some waveforms that they show the derivatives of. And, that's interesting, but we don't need to camp on that. Here's the op-amp portion. We're skipping that. Binding of capacitors and inductors, which you already had. Now we get into this last part, which is the initial conditions part, which is when you first start up, what are they, and after a while, what are they? At t equals 0, and t equal at a higher after a while. We've done that before. Now we get into the problems. Okay, so the problems into chapter 6 use those equations, and I'm going to skip the part about power, but I'm just going to ask you about the voltage. What would be the voltage across here? Okay. Voltage across a 1 microfarad capacitor is 10 U of t. Okay, so 6.1. The voltage across a 1 microfarad capacitor is 10, so it's 10. It starts at 0 and it goes to 10 volts. Okay. Derive the expression for I of C and PC. Well, is the capacitor absorbing power, delivering power, or both? So what's IC? I of the capacitor is equal to what? How would you graph it? This is voltage. What would be current? They don't talk about it, but right at t equals 0, it goes really high in spikes, okay? I equals C dV over dt. But after that, it goes back to 0. Why does it go back to 0? Because the derivative of a flat line is 0. There's no change. The derivative of a constant is 0. Okay? The derivative of 10 with respect to dt is equal to 0. Any questions? That one's that, okay? Now this is this Dirac delta thing. It spikes and goes way high, and then it comes back and is at 0. Now that's for a perfect signal, and that never happens. That never actually happens. We always get something like this, or we always get this, and we get this, or whatever. But it does. This is a perfect case, okay? So it can't happen, but we're just saying it can. Anyway, that is I for that circuit. 6.2. All right, 6.2. The voltage across the 10,000 picofarad capacitors V is 100 sine blah blah blah. Derive the expression for I of C and P of C. So now 6.2. All right, so we've got a 10,000 picofarad, which is equal to what? Equal to 10 to the minus 8 farads. So that's our capacitor. So this is minus 12, 11, 10, 9, 8. So it's minus 8. Okay, so, and the VC is equal to 100 sine of 2 pi times 10 to the fourth t. What is IC? I equals ice. I equals C dV over dt. So it is this 10 to the minus 8th derivative of sine, which is what? Sine, right? It's 10 to the 8th. So it is, so it's 10 to the 8th times 100. That's my constant out front, times cosine of the derivative of this, which would be what? You bring out the 2 pi times 10 to the fourth, and then 2 pi times 10 to the fourth t, right? So you have, in essence, 10 to the 8th times 10 squared times 10 to the fourth times 2 pi times cosine of 2 pi times 10 to the fourth t. That's the expression for I of C. So what is that? 10 to the minus 8th, 10 to the fourth, 10 to the 2, so it'd be 10, it's 2 pi times 10 to the minus 2 cos of 2 pi times 10 to the fourth t. Any questions? Everybody see that? And if you want to, you can multiply that and figure out power, but I'm not going to, again, power is messy. I'm just going to leave it alone. But at least you got the ice part of it and the Eli part of it. Any questions about that one? 6.3. Does that make sense? Okay, the current through a 0.2 microfarad, 0.2 microfarad capacitor is a rectangular pulse with an amplitude, there's a rectangular pulse with an amplitude of 3 milliamps and a duration of 5 milliseconds. So it's 3 milliamps and its duration of 5 milliseconds. Okay. Find the capacitor charge voltage at the end of the pulse when the capacitor voltage at the beginning is minus 50. All right, so what would that be? Well, if I equals C dV over dt, what would be V?
the integral of I divided by C?
Yep, it's, you take the, okay, so you take the integral of this, 1 over c, move the c over, and that's the integral of that. So that would be that, plus v of 0, v at 0, or v print 0, okay? So, what would be the integral of that signal right there? Well, it's the integral, it's 1 over c, which is, what is c? It's 0.2 times 10 to the minus 6, so it's 1 over that. And then it's the integral of 0 to 5 milliseconds of 3 times 10 to the minus third dt. Okay? Minus 50. What would that be? Well, it's 3t, so it's 1 over 0.2 times 10 to the minus 6th. Evaluated at 0, it's 3t, evaluated at 0 and at 3 milliseconds. And this is 3 10 to the minus third times 3. So what would it be evaluated at 3 milliseconds per t? It's 3 times 10 to the minus third. So you've got 1 over 0.2 times 10 to the minus 6th times 3 times 10 to the minus third, which is this, times 10, excuse me, 3. This is my 3 right there. This is my 10 to the minus third right there. Then at t, it's 0 to 3 times, there's another 3 in here, 10 to the minus third times 3. What would that be? Yeah. There's a minus 3 and a minus 3 and a 3 and a 3 and divided by 0.2. What's 9 divided by 0.2? Wait a minute, is that, or maybe I've got 3t is, oh, it's 5. I'm sorry. This is 5. I wondered what the heck is going on. This is 5 milliseconds. So it's 5 times 3. So it would be 15. What's 15 divided by 0.2? 15 divided by 0.2 is 75. But I've got a minus 50. What's my final answer? 25 volts. Are they all this hard? We don't go very far in this chapter. This is about as far as we go, okay? Any questions about how you do that one? Okay, so that's how that one's done. Number 4. Now, number 4, you say, what is he getting at here? These are not bad. These number 4, this kind of question, and number 5 isn't that bad, I don't think. Maybe you don't like them, but some of these are stinko, but 4 and 5, not that bad. Okay, so if you look at this and say, now what are we going to do here? Number 4. The voltage across a 0.001 microfarad capacitor is shown in that problem. Okay. Prepare sketches for I of C, and that's where I stop. Okay. So what would be, it's a 0.6.4, 0.001 microfarad capacitor. Okay, so 0.001. Prepare the sketch of IC. So what would it look like? All right, so I equals C dV over dt. What would it look like? If this is coming up, it would look like a what? It's a constant ramp function going up. So what would be, okay, so what is dV?
40.
Okay, so it's 0.001 times 10 to the minus 6th. So this is a constant, but what is it? What's the dV? It's 40, right? The dV from 0 to here is 40. What's the dt? 100 times 10 to the minus 6th. All right? So I've got 0.001 times 10 to the minus 6 times 40 over 100 times 10 to the minus 6. So the 10 to the minus 6 go. So I've got 40 over 100 times 0.001, or what? 0.4 times 0.001, or 0.4 milliamps. So it's a constant at 0.4 milliamps. Does everybody see that? That is a good test question. Everybody follow that? You don't have to do the integral, you don't have to know calculus, you just have to look at dV over dt and look at the equation and you can get it. Does everybody see that? Now what is it here? What's your dV over dt? 0. What is it here? It's a negative number, isn't it? It's going from 200 to 400 and it's what? Minus 40. So down here you are at 0.4. Up here, what are you down here? No, I'm sorry. It's not that. Oh boy. So I gotta erase. I gotta go back and erase. So it went up to 0.4 there, but here it goes down 40 over 200, which would be basically half of that. So basically now I've got half of my rate, which was 0.4, and from here to here it is what? So this is at 1, at 2, at 3, at 4. Here it is minus 0.2 milliamp. You ever see that the rate goes half the rate of this one? This goes up 40 over 100 milliseconds. This goes down 40 over 200 milliseconds. So this is half of this, 0.4 minus 0.2. Done. That is the kind of question this chapter asks. That's the kind that you should be able to answer right there. Okay, now the next one is 0.01 microfarad capacitor, blah, blah, blah. Show the value, the sketches of I, and then forget about P and W. The capacitor is absorbing or whatever. If it's a positive, it's absorbing. If it's a negative, it's letting it go. That's how this works. Okay, so what is up here? Voltage across. Okay, the capacitors. What would be right here? This is a rate, right? And this is in milliseconds. So what would be my 6.5? What is my capacitor? 0.01 microfarads. So that's equals 0.01 times 10 to the minus 6th. What is C? Or excuse me, I. I equals C, 0.01 times 10 to the minus 6th dV over dt. So the dV is 10 volts. The dt is what? In seconds, it's 0.01. So what is I? I is 0.01 times 10 to the minus 6 times 10 divided by 0.01. The 0.01s go away, and it is 10 microamps. In that range. And I'm not going to do the rest of these for you because you can do them. Any questions about that? Yes, this is the kind of stuff that you're going to have to answer on a test. Not hard, but just crank through that I equals C dV over dt, E equals L. The same thing but different for the inductor. But this is what you're going to have, this kind of stuff. Not hard. This is another, 6 is another, 6 and 7 are the same kind of thing, only this is a cosine one. Okay. Do the best you can. I'm not going to grade off on these. If you just try, I'm not going to grade off. 15 and 16 are the same thing for an inductor. Oh my goodness. Okay. And just I, don't do anything else. Derive the expression for I. So what would it be for this one? Eli, right? Eli and Iceman down. You get through all of these without hardly any difficulty. But that's asking you to be able to do that. So that's asking you to say, I can solve a first order differential equation, or basically, okay, so what does this do? So this is basically so you can forget this part of it, other than the inductor, okay? So initial condition of 20 milliamps so initial condition is 20 milliamps, so up until time equals 0. At time equals 0, this is it. So what are we saying here? Eli. So I, how do I get I? I equals what? 1 over L integral volt dt, okay? Plus V0, plus I0. What is I0? 20 milliamps. What is the integral of this? Well, it's this, minus 6 e to the minus 1,000. 3 zeros t. So what is the integral of that? It's 1 over 1,000 e to the minus whatever. And that's how that's done. You don't have to do this one if you don't want to. If you like doing these kind of questions, you can. This one is a cosine. 15 and 16, I will not ask you on a test. Okay? The kind of questions I want to ask you are the ones that I just highlighted. So again, if you don't do 15 and 16, no big deal. I'll give you those two. Okay? You can skip them. If you want to do them, it's fine. If you don't want to, you can skip 15 and 16. And there's the rest of them. Scanning through the chapter for you to see what's all been asked. This is a dirty part of this course. It just takes time to get into the hard part, but this is not easy because you're being asked to do things that you kind of have to dip back into your calculus, and you say, is he going to ask me a hard question on calculus? The answer is no. I'm going to ask you questions that have to do with this kind of stuff like this, And I doubt if I do any of the integral stuff, I could, but it's mostly just this stuff right here and graphing. That's it. But once you get that, that's about all you need. You don't need all this other stuff. And why are we doing this in the first place? For the initial conditions, and also to ask the question, what is going on in a capacitor and an inductor if it's not a sine wave or not a cosine? If it's not a sine wave, what is going on in that capacitor or that inductor? Why do we get a kick? Why do we have to put if you have a coil, a relay coil, why do you have to put why do some people put a backward flowing diode in it? So when you put 24 volts plus to minus, this flows, right? And you get a relay action. But when you turn it off, what happens? That current in that has to go someplace until it dies. And you want it to do this until it dies. If you don't, what happens? It goes somewhere. It'll go anywhere it can, and if there's a transistor in the circuit someplace downstream, it'll blow it up. Say what? It will mess with it. It'll work a couple times and then it'll go away and it'll never come back. And you'll say, now what happened there? Oh, it's that stupid inductive kickback, or then it's Eli. E equals L di over dt. Can't go to zero immediately, or else you're going to have an infinite spike of voltage. And infinite spikes of voltage are very harmful. So that's why we do this. It's not just because, oh, these are good math problems. No, I believe there's a real rationale for these problems to exist, other than the fact that, yeah, they're here. We don't want to mess with you too much and give you, too many headaches, but we do want you to understand that this is real life, real problems, and occasionally they can come out and bite you. Although, it's very rare. Most of the time you get away without having to do anything, worrying about any of this, but every once in a while, you do. And when you do, it's like, what just happened? I could ask the question of my furnace the other day. My wife said, it's getting cold in the house. I said, no, it's not. That's your imagination. I didn't say that. I thought it. And she's always more, into that stuff than I am. And I just kind of looked at her and said, whatever. I didn't say that, but I thought it. So again, I admit that pretty insensitive to that stuff. But I did, after a while I said, it is getting cold in the house. So I went outside and looked, and I looked downstairs first, and it had this code, which is a pressure sensor code. And what on earth? It's a pressure sensor somewhere. So I thought maybe there's snow on the thing. I went outside, and I shook them. The input, the intake and the outtake. Okay, the two pipes that come out of the house. One takes the air in, one takes the air out. One takes the exhaust air out. Okay, so I took them and banged on them a little bit. I didn't bang on them too hard. I didn't want to tear them up. But I came back in and nothing. Still cold, getting colder. About 10 minutes later, 15 minutes later, it kicked on again. What the heck happened? Did I fix it? I'll claim that I fixed it. I have no clue. But again, I did what I could, and it worked. Something worked. I don't know what worked, something. But I'm telling you that because sometimes you don't know. All right, so why are we now studying this circuit? Now we're not going to go all the way through this, except for the fact that we're going to, again, do the first order RC and the RL circuits. Okay, so we're gonna go back and we're gonna camp on those just a little bit. If you remember me from 1020, this is we went back into the first book, the 1010 book, and we actually studied these, and we said, you know, you do need to remember this. And the only reason we need to remember this is because these are pretty straightforward. This part right here is the part that the initial conditions, the initial and final conditions are the part that you have to do in order to solve Laplace transforms. So if you're taking the EET 4450 class, and if you're taking it from me, you get hit with Laplace like a brick bat. Okay, it's there, you gotta do it. And in that course, we give you initial conditions. If there's initial conditions, and you hope that there aren't, but if there are, here they are, okay? They're given to you. But in this course, you have to find them yourself. And the big difference between this course and that course is right there, initial conditions, initial and final conditions. So you say, no, you're telling me that we're taking the same course twice. Yes, you're going to use the same sheet. You're going to use, if you're taking or have taken EET 4450 from me, you'll take the same sheet, and we're going to go down and we're going to look and we're going to figure out, do we have to do separation of variables? Can we do this without separation of variables? Can we, how do we crack this? But with these, RC and RL, we just solve it. We don't even go there, okay? But the initial and final conditions part of it, you have to come up with because, and this D term, remember that the integral, the second integral of something is the derivative of something, the solution, there's two of them, and you have to get the D. And how do you get the D term? How do you get the D term? How do you think you get the D term? ICE, an Eli. So you have to know that in order to get the initial conditions. And that's the only reason we're doing this, okay? But chapter 7 is a review of RC, RL, and initial conditions. And then they go down and then they do a first step at this, which I don't think is necessary. Now, there are some things in this part of it that are good, but I can skip this, okay? I can skip this because you get it again in chapter 9. This part right here, I can kind of go through and kind of skip and say, well, we're going to get it, but we're going to get it again, so we're just going to skip it for right now. We're going to use Laplace on this. He or she kind of uses Laplace, and then they back off and they say, well, you can just get a standard equation. Here's a standard solution for this problem. Standard, 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 standard. But again, there's nothing standard. So we can kind of just chuck this and forget about it. But this part we can't. All right, so that's chapter 7 in a nutshell. So if I have a resistive capacitive circuit or a resistive inductive circuit, I can solve it using a first-order differential equation. What is the equation? Well, it's this one right here. It's this equation right here, which gives you a solution of what? That. Or either that or it's either this or this. Okay, so what's the difference between this one and this one? This is the this is the e to the minus t over tau. This is the 1 minus e to the t over tau. Okay, what is this? This is the charging circuit, this is the discharging circuit. This is the one with the voltage supply in, this is the one with the voltage supply not in. So this only works if you have a DC supplied circuit, okay? And one R and one L or C. It's got to be one or the other, but it can't be both. And the circuit's got to look like this. Or it's got to look like this. But with that in mind, this works. So if you're looking for that solution, this works. And that's from the last part of EET 1010 and we did it again in 1020. I'm teaching them right now the same stuff. So if you wonder, why did we bark about that? It's a standard solution to a standard problem. But it comes from this derivation right up here. This right up here, right there. That's the inductive one. There's the capacitive one as well. Okay, so that gets you the why we do this. Now, if you have more than one inductor, you have to combine them. If you have more than one capacitor, you combine them. How do you combine capacitors? Use the parallel rule. For series, use the series rule. For parallel, it's the opposite of resistors. If you have inductors, it's the same as resistors. Okay? How would you combine these two? They're in parallel. So you basically use the parallel rule. And how would you find the resistance here? You would use these are in series, but this does not show you that they don't always show you the battery or the supply, and in that case, if it's not there, then you're using the decayed one. All right, so again, this is the problems that you have, and you know, this is all the theory. But when they get down to it, down at the end of the chapter, it's the same thing. And I think I picked the number of problems that you need to do for this chapter, and it is, I don't think I wrote them down in here. Yes, I did. There's a bunch. So I did chapter 7, 1 through 15, 37 to 40, and 42 to 46. So there's a bunch. Try them, work on them, especially the first 15. And I'm not going to go through those with you today, but that gets you at least started on these problems. Okay, so I'm going to go down here and I'm going to just scan them for you right now. Okay, so you can work on them if you don't have a book. So we're going through chapter 7, and then I'm going to pretty much when I say it gets harder, I don't mean really, it doesn't get a lot harder because we use Laplace, and if you've done Laplace before, we don't do anything new. We're doing the same thing that we did in EET 4450. So you're not doing anything new, you're just finding initial conditions, and that sometimes is a little harsh, but it's not that bad. And again, we give you a sheet to write down things that are in like, we give you a crib sheet, or you have your own crib sheet that you build over the course of this course. And on that crib sheet, I'm going to tell you some things you need to put down. How to do initial conditions in a capacitor and inductor is extremely important, okay? So we missed Monday. We would be through this if we didn't have that. But I'm just scanning down through this stuff so that you can look through it at your leisure. And again, I'm not trying to do everything in this, but I do want you to understand that the initial conditions are important. We tend to steer clear of too many of the sine and cosine equation type problems, but again, we do occasionally use one of those, but probably not on a test. And there will be a review before the test. although there will be a test. There's really 3 tests in this course, and then a final. So get used to them, because they're gonna come, and they ain't easy, but they're just these problems. All they are, the problem that I gave you on the quiz 1, the, the ones that I stress, and, I'm gonna tell you, I don't understand, and I don't wanna understand everything that's going on here. Now, this is the development of the, quadratic equation. So this is the part that they do again in chapter 9. So it's the same thing, except it's in a specific circuit. So they pick a circuit, they pick this parallel circuit, and they pick the series circuit, and they solve it. But, but, we're gonna do that again in chapter 9, and I don't think we have the time to go through that in detail here. Although it's a special case, it's just, if you just have the 3, an L, an R, and a C in series, if you just have the 3 in parallel, an L, an R, and a C, what would it look like? What would your signal look like? Or what would your voltage look like? Well, or what would your currents look like? Whatever. And that's basically solvable in chapter 9 with Laplace. So we're not going to worry about this part right now, even though, yeah, it's a quadratic equation, and they show you how to do the quadratic equation, and you get this, you get the real and imaginary part, and then you can graph it, and that's nice. But there's more to it than just that, and I don't think we have the time to go into it in depth right here. Even though it's a series and a parallel RLC, right? With a simple battery, or a battery power supply. Or maybe a sinusoidal supply, but it's just basically a battery supply. There's a battery, and then find all that stuff. And in this case, the resistor is in series with the inductor and the capacitor. And they find the solution. There it is. But, what a mess. And it's much easier solvable in Laplace than it is here. Why don't we just wait until Laplace? Well, he wants to introduce you to the quadratic equation, and that's good. And if we're, whatever, it does do some good to bring it up here, but again, let's just use Laplace, be done with it. Hit it with a big hammer and be done with it. Yes, you're going to be writing current loops in Laplace. Okay, so you're going to be writing a current loop equation with differential equations. But immediately you're going to turn it into an S, or 1 over S. So that's what Laplace is about. Okay, so there's your summary, and then your problems. This first part, 1 through 15, is just the either an R with a C or R with an L, and that's all this is about. And this is a review. That part is a review of your 1010 course. How do you combine that type of thing? Here's an example. Oh my goodness, how do you do this? And then we go down to 37, and down there we do another little bit. And we're done. 37 to 40. Uh, Forget about these. Forget about 37, 38, 39, and 40. That part of it, I can do without for right now. 42, 42 is the same as before, but 42 is a good one. 42, uh, 42 is the only one that I'm gonna ask you to do back there, so, again, don't worry about any of these other ones. We'll go back and we'll look at the rest of them, but 1 through 15 and then 42, and that's it, chapter 7, and you're done, okay? So I'm gonna redo that. And have fun. Try to work on some of these. I'll send you another quiz, probably in the mail, probably over the weekend or sometime, and hopefully by Monday, you'll have it, and you'll be all set. Okay? Take care. Have a good day.